In this video, we are going to discuss about kernel fusion. We are going to see what's kernel fusion and why it can lead to speed up. And we are going to compare some benchmarks for fused and unfused kernels. And then we are going to see the applications of kernel fusion in deep learning. Let's start with a very simple example. We want to compute a star x plus b, where a is a scalar, x is a vector of size n, b is a vector of size n, and as a result, z is also a vector of size n. Now, doing it in an unfused kernel simply means that we are launching multiple kernels for doing this computation, where in this specific case, we are launching this two kernels. One kernel is computing this constant and vector multiplication, and another kernel is doing the vector addition. While doing it in a fused kernel simply means we write a single kernel, which is going to do the complete computation. Now let's try to understand the memory aspects involved in this unfused kernel case. So in this case, we are loading the X and A from the global memory. Kernel 1 is doing that and then doing some computation over them and then storing the results back to the global memory. And then kernel 2 gets launched. It's going to read the temp and B from the global memory and then restore the results back into the global memory. While doing it in the fused kernels means that we're going to read X, B, and A directly from the global memory and store the results back into the global memory. Let's try to compare these two cases. So in this case, we are going to allocate some extra memory called temp in the global memory in order to store our intermediate states. And then we'll have to read and write, do extra reads and write in order to use this temp variable. While in this case, we are going to read only the important variables from the global memory. So there is no intermediate state involved in this fused kernel case. Let's try to see some code. So in unfused case, we are simply doing this. We are simply having these two kernels. One is doing the multiplication, constant multiplication with a vector. So each thread is going to read a single element from X and A, and then it's going to do the computation and then store the results back into the global memory. And then we have this second kernel called add, in which we are going to, each thread is going to read a single element from these two vectors, do the computation, and then store back the results. And then we have this unfused operation, which is combining these two kernels. So we allocate this extra temp memory using qdmalloc, and then we launch these two kernels in appropriate manner. So we can clearly see in this case, we are going to do 3 reads and 2 writes, which is total 5 operations. And then we have to allocate this extra temp buffer also in order to do our computation. While in case of fused case, the code is quite simple. Each thread simply reads X, single element from X and B, do the computation and store the results back to the global memory. There is no temp variable, extra allocation, and there are only 3 reads plus writes operations involved. So we did benchmarks and found that we did benchmarks for comparing these two cases on a same machine for different input sizes. These are the size of X and B, and these are the time measured in some dimension. We found that the unfused case is twice as expensive as compared to fused case, and we have already stated the reasons before. Let's try to summarize things. But before that, let's think about, did we miss anything here? Yes, we did. So if we think more, we can clearly say that there is an implicit synchronization involved in this unfused case, and we need to be really careful while writing the fused kernel to handle synchronization whenever necessary. Let's take another example. Let's say we want to do this computation. Now, if we do it in unfused case, it's very simple, right? We can just do this thing and then do this thing. And then when we launch these two kernels, there is some kind of barrier because the kernels are always launched in a sequential manner. But if we do it in fused case, we can't directly write these two statements because there will be a data race involved in these cases because second thread may read before as compared to the first thread, assuming first and second thread are from different warp. So we need some kind of synchronization. In this particular case, let's assume we are doing launching the kernel with the same block. So we are just going to use the sync threads in order to do our computation correctly. So let's summarize everything. Without kernel fusion, we'd have to allocate extra buffer to store the intermediate state of the computation. we would need to access same elements multiple times from the global memory across multiple kernels. And we can clearly see that the bandwidth for accessing the elements from the global memory is very low as compared to accessing the elements from the registers. So we need to really if you want to speed up things, we really need to reduce the accesses from the global memory. And then there would be some kind of overhead in launching multiple kernels, which is happening in our unfused case. Also, any cache or shared memory related to the kernel would be deallocated once the kernel execution is over, and we can't make use of the shared memory across kernels. Let's try to understand the applications of kernel fusion. So one of the big application of kernel fusion is in deep learning. But the main issue is that deep learning graphs are very big and we can't really fuse the arbitrary computation. In our case, we were able to do that. But is it possible to write the arbitrary kernels for each and every computation we want to do? Right. It's not possible, right? So there comes the compilers like XLA by Google. So Google has made this compiler called XLA, accelerated linear algebra, where it's you just need to specify JIT compile equals to true in your tf dot function as an argument, and then XLA will take care of everything. Internally, it does a very simple thing. It simply searches what all operations can be fused together, and it simply does the fusion and do these operations in a single kernel. So in this particular case, these two operations are fused. XLA found it can be fused, so it rewrites those two operations in a single kernel. Similarly for these three operations. I copied these benchmarks from the TensorFlow website. You can clearly see that with XLA, the throughput has increased to a very big number as compared to the without XLA case. Thank you so much.